Okay, here we go. I'm going to be going through practice problems for Chapter 6 elements. These are just taken from our class materials. And if you, I recommend when you're going through these that you try to solve the problems on your own first and then watch the solution, just so that you've had an attempt to practice. Also, if you haven't had a chance and you're not 100% sure on these topics, definitely go check out my quick review of SN1, SN2, E1, E2 video that goes over everything. But just real quickly, I'll say that when I'm trying to determine if something's an SN1 or an SN2 reaction, I'll check for the nucleophile to be strong or weak, and I usually will just basically look for negative or positive. That's generally a good indicator. If it's secondary, or if it's strong, then it'll go for the 2s. So that would be SN2 or E2. And if it's weak, it goes for the 1. So that's SN1 and E1. If it's a narrow primary or secondary, it'll go for SN2 if you have a strong nucleophile. If it's got heat, if it's bulky, or secondary or tertiary, it's going to go for E2. Now for the 1s, that's harder because the first step for both of these is a carbocation. They are probably going to be, the first step is going to be a carbocation for both of them. You got to look out for rearrangement. And then if it's narrow, it'll go for the SN1. If it's got heat or bulky, it'll go for the E1. But in reality, a lot of these they'll end up being close to the same ones. Let me clarify what I just said again. In reality, when you do, I was sort of distracted. In reality, when you work on these, in real life, if you put these together in a Erlenmeyer flask or whatever, you're probably going to get a mixture of these. But most of the time, we're looking for what the predominant reaction would be. Sorry, I got totally distracted by a message that came in on my computer. Okay, so that's just my brief overview. Now we're going to hop right into it. If you want a longer explanation of that or the reaction mechanisms for all the different SN1, SN2, E1, E2, check out that other video. Okay, so the rate law for the following reaction. Before we can do the rate law, we have to know if it's SN1, SN2, E1, or E2. So for the SN1 reactions, so the first thing we're going to check for this is the nucleophile. So the nucleophile here is negative. So I'm going to say that is a strong nucleophile. And we could, look at the fact that this is secondary, there's no heat, this is a pretty narrow nucleophile, and assume it's going to be an SN2. So it's a strong nucleophile, so it goes to the 2, so it's in either an E2 or an SN2. It's secondary, could go either way, but there's no heat, and it's a more narrow nucleophile, so I'm going to go with SN2. But really, you don't even have to do that, because here in the reaction, it already shows you. I'm going to draw this out for you. 1, 2, 3, 4. All right, 1, 2, 3, 4, 5. You have a bromine, and it becomes an alcohol. So there's no double bond form, so this has to be a substitution rather than elimination. So I know that for a fact that this is SN2. So if this is SN2, then the rate it's a one-step reaction, and the rate depends on the 2 molecules involved. I talk about that more in our other video as well. So the rate is going to be determined of the substrate with the leaving group on it. So I'm just going to write leaving group. That's easier for me to remember. And the nucleophile, which is this OH. The nucleophile attacks, kicks the bromine out, and forms the new structure. So the rate law is K times the concentration of the leaving group and the concentration of the nucleophile. So the leaving group, they put in RBR, just that is R is any carbon chain like this, bonded to a BR. And then the nucleophile is OH minus. So that should be answer choice B. Now, in this case, if you were to double one of these 2 things, that would double the rate law. If you were to double both of them, it would quadruple the rate law. Just something to check out. Also remember that for SN2, there's an inversion of stereochemistry because it attacks from the backside. So if this was a wedge, the OH would be a dash. Now this one tells you it's SN2, but if you just want to check yourself, this is OH minus, so negative charge indicates that it's probably going to be strong, so it's going to go secondary. And then this is primary, So it's probably going to go SN2. There's no heat, so there's nothing that yields it to E2. So it's probably going to be an SN2 reaction. So that's right. So we checked ourselves and it was right. I'm going to draw this out. 1, 2, 3, 4. Br plus OH minus yields to OH plus Br minus. So what happened here? This attacked, kicked this out, and we ended up with this plus our Br minus. So the rate law of this reaction, the one with the leaving group and the substrate, which is, or the nucleophile, which is OH minus. So the question is, assuming no other changes, what effect on the rate would result from doubling both of these concentrations? So the thing that would result from doubling both of these concentrations, well, if you multiply this by 2 and this by 2, to even it out on the other side, you have to multiply it by 2 twice as well, which means you're multiplying it by 4. So it would increase the rate 4 times would be the right answer. Okay, last question on this page is select the potential energy diagram that represents an exothermic reaction. So energy is going up. What happens in an exothermic, I just made up a new word, electrothermic. An exothermic reaction is your energy as the reactants is higher than the energy of the products, right? So this is a higher energy than the product. So energy is being released. Endothermic energy is being put in. Exothermic energy is being released. So by some path, it doesn't matter if it goes up and down a bajillion times, if it doesn't go up and down at all, as long as your products have a lower energy than your reactants, then this is going to be exothermic. So really all it's asking you for is, do you know the definition of exothermic, and do you know that the products have to be lower than the reactants? And the only one that has that is answer choice E. So it doesn't matter how many steps or anything in between. If we're just looking at exothermic, we're looking at starting and finishing. Okay. For the next question 4. Let me flip to it in my notes just to make sure. So for question 4, it's asking, what would you expect to obtain from the following SN2 reaction? So it's telling you it's SN2. You don't have to go through this. If you want to, just to check yourself, you always can. If it's an SN2 reaction, our nucleophile, this CH3ONA is the same thing as CH3O minus and Na plus, just hanging out to counteract the negative charge. So I just get rid of it and don't pay attention to it much anymore. So this is going to attack the carbon where the leaving group is attached, and it's going to kick out that bromine. So because it attacks where it did, that's why it's a backside attack. So we get an inversion of stereochemistry. So it's going to be attached on the top. It's going to sort of shift that hydrogen down to be on the bottom side, but the other side will stay the same. And if you want to know more about that reaction mechanism, I go through that step by step in the last video. So this would be our right answer. It happens all in one step. The rate is the nucleophile and the substrate. You can write sub or leaving group, whatever works for you, times K. And our product is going to look like this. So the only answer choice that gives us the right product is answer choice B, or 2. Answer choice B. Okay, next question. The major product of the following reaction would be what? Again, you don't even have to waste time figuring it out. If it's SN1, SN2, E1, E2, that's nice. They tell you. So what happens is this is going to attack where the leaving group is attached and kick the leaving group out. So it's going to attack, kick the leaving group out. So the only place where the stereochemistry is affected should be right where the carbon attacks. Students get this mixed up a lot because they're trying to trick you, I feel like, here. This is not going to change stereochemistry at all. The carbon attacks right here, or the alcohol attacks right here at this carbon, where the chlorine used to be attached. And it's not a stereocenter because there's already 2 hydrogens there. So it doesn't have 4 different things attached. So there's no change in stereochemistry because there's no stereochemistry because it's not a chiral center. So the right answer is actually going to leave the bottom half of this molecule the same. So that would be, this one flips the OCH3 over, so that's not right. This one keeps the OCH3 where it is. There's a CH3 down here and a hydrogen here. This looks like the right answer to me. Just in case I'm going to check. This changed the bottom one completely. This should be OCH3 and didn't replace the leaving group at all. OCH3 is not going to be a good leaving group, so that's why it goes to where the chlorine is. And then same thing right here, it attacked in the wrong place. So the only one that got the right attack on the leaving group, the chlorine, is answer choice B. So that should be your right answer. Okay. Question 6. Consider the substitution reaction that takes place between 3-bromo-3-methylhexane. So I'm going to draw that out. 1, 2, 3, 4, 5, 6. 1, 2, 3. I'm not going to draw the stereochemistry right now because I doubt it's going to be relevant to this question. If it's an SN2 reaction, there will be an inversion of stereochemistry. If it's an SN1 reaction, it'll be a racemic mixture. So I just will remember that. So it would go from R to S, basically. Consider the substitution reaction that takes place, with sodium methoxide, OCH3 minus. Which of the following would be true? Okay, well, OCH3 minus is negative, so I'm going to assume it's strong. And then for secondary, or for the SN2 versus E2, this is a tertiary leaving group. So if the leaving group is tertiary, this is going to go E2. You can't have a tertiary leaving group on an SN2 reaction. So this should be an elimination reaction, would be my guess. So the only possible answer choice would be answer E. The rest of them don't have an elimination even taking place. So that is not going to be the right answer. Pretty sure a spider just jumped on me. Okay, sorry. Question 7. By analyzing the starting material and the products, the following reaction is an example of what type of mechanism? Well, this is substituted. So you can go ahead and assume it's a substitution reaction. An elimination creates a double bond. That's not happening here. We're substituting Br for N3. So you already know it's a substitution reaction. Now, is it going to be SN1 or SN2? Well, this is N3 minus, so that's strong. So I'm going to go ahead and say it's SN2. Just based on it being strong, it's going to go here. And I know it's strong, or can assume pretty well that it's strong because it's N3 minus. Okay, question 8. Which alkyl chloride, though primary, is essentially unreactive in SN2 reactions? Okay, so all these are primary chlorines. It's tough because it's fluid. All these are primary chlorines. So you're asking which one's not going to react very well in an SN2. Well, SN2 needs a backside attack. So this has a lot of steric hindrance on it. So it's not going to be really easy for the nucleophile to come in and attack here. So that big bulky group really hinders it. So this is an interesting one because technically it's a primary. If you just followed the rules and didn't use your critical thinking skills, it would be really hard to process that. But if you can just think critically about an SN2 reaction, does a substitution, it's going to do a backside attack, and the backside of this is pretty bulky, then that's going to probably jump out as the right answer to you. Okay, which of the following is not a nucleophile? A nucleophile loves nucleuses because it has a lot of electrons. So it wants to find something that doesn't have a lot of electrons and give it its electrons. So it has to have electrons for that to happen. So here's the structure of water. Here's the structure of methoxide. Here's the structure of NH3, and here's the structure of NH4. There's only one that doesn't have extra electrons, and that's NH4. So that's your right answer. So for that one, I mean, that looked really simple, right? But you had to know the definition of a nucleophile. You had to know these structures off the top of your mind and remember that there's extra electrons there. So this is really building on the last several chapters that we've worked on. Okay, the next question is about nucleophilicity or nucleophile strength. So this is actually a kind of a tough one, I think, because it's so hard to know which is the strongest nucleophile. I struggle with this. So I recommend you go to your book, page 265, and read some about that. And then further down, this is for the 11th edition, so I hope this is right for you guys. Further down on page 267 or 268, and 268, it's like the bottom of 267 and the top of 268, they talk about nucleophilicity strength. This one talks about it in terms of the solvents. And then this one just talks about generally. So one thing about nucleophilicity is if you have a negative, that is always going to be a better nucleophile than its conjugate. This base is always going to be better than its conjugate acid. So if you add a proton to it, the base is always going to be better than the conjugate acid in terms of it's going to be more nucleophilic. If you have a series like we do here, where the nucleophilic atom is always the sulfur, all these, we're looking at this sulfur, then you can just go according to the same thing you would look at as if you're trying to determine which is the most basic. So that's one rule, is the negative is always better than the non-negative. The second rule is if they're all the same, nucleophilicity is the same as basicity. But if this was a sulfur and this was an oxygen, then it wouldn't necessarily parallel basicity. And if you have a series of atoms in a different solvent, that's going to impact the nucleophilicity differently as well. But we all have sulfur here, so we can just basically look at this as the same as a base. So we can know for a fact that this is going to be the most positive. So this is not nucleophilic. So this needs to be the last one. It is the least nucleophilic. So if you just know that positive is not nucleophilic, you can narrow it down to answer choice A or C. So that's pretty incredible. The next thing you need to know is what I like to call the R substitution principle. This is not a real principle, I just made it up. But the way I remember it is alcohol is ROH and water is HOH. And I have these pKa's memorized. Water is 15.7. Alcohol is just a little bit more basic at 16 to 18, something in that range. Okay. The same thing is going to be true here. If you have RSH versus versus HSH, which is what you have, it's going to follow the same trend. So this one is going to be a little more basic. I don't have these pKa's memorized. I have no clue what they are. I had to go look it up. But because I have these memorized, I know that this is going to follow the same trend. And R substitution will make this a little bit more basic than just having a hydrogen there. So this, with an R substitution, is going to be slightly more basic than this without the R substitution. We also know, just based on the rules from nucleophilicity, that this, and because negative charge are automatically more basic, that both of these negatives are going to be more basic than or nucleophilic than either of these. So I'm going to rank it the CH3S negative, then the HS negative because of this principle down here, then the CH3SH because of this principle down here, and then the H2S. So both of these start with 1, but 4 being the next most basic puts us in the right category. Now, if you just knew that positive were not nucleophilic and negative were nucleophilic, you would get this right. But I wanted to walk you through this because a lot of times before exams, I'll say something like, use what you know to eliminate the answers that are definitely wrong. And you knew already, theoretically, hopefully, the pKa of alcohol and water. I don't expect you to know these pKa's off the top of your head, but you can use what you know to make inferences about what you don't know. And that is going to help you on the exam. Okay, so this question, question 11, this is the one that's addressed on 267 and 268. Basically, if you have this tiny one as F, if you have I minus, Br minus, Cl minus, and F minus, and you're in a protic solvent, my camera keeps drooping down and messing me up so that you can't see everything. And you're in a protic solvent. The protic solvent, so say it's water. So I'm going to draw these circles as if they're water. I'll make them blue. How about that? If you have water coming around here, a bigger atom, which you learned about radius size way, way back in general chemistry, is going to be less inhibited by a smaller atom that gets the same water molecules around it. And part of that is this F minus is not distributed very big, while this I minus, it's the same negative charge. There's one minus on both of these is distributed on a much bigger surface area. So this is less negative all around, and this is very negative concentrated. So these water molecules are going to be drawn to that. So actually, when really F minus is a stronger base than I minus, if you get rid of solvent considerations, in this case, if you're in a protic solvent, I minus is going to be the best because it'll be the least inhibited by the solvent. That's kind of confusing. I highly recommend you read this little section. I think it will help you a lot. That unlocks some doors for me. I just realized I answered this question wrong. I said this would be the strongest, which is true because it'd be the least inhibited. But the question was asking for the weakest one. So I would have got that wrong on an exam. So be sure that you check for those keywords. So the weakest nucleophile is going to be the F minus because it's the most inhibited. So this is the wrong answer. This is the strongest. I was not even paying attention, so I got that wrong. So I'm sorry. Should have been paying attention. If it helps you to make sure that you've got it, I can say this is the strongest and this is the weakest. So strongest to weakest in protic solvents only. Okay. Next question, question 12. An SN2 reaction will occur most rapidly in what mixture of water and ethanol? So this is protic. So we're still looking at iodine being stronger than bromine, being stronger than chlorine, being stronger than fluorine in terms of nucleophile. So the stronger the nucleophile, the faster the reaction will go. And then you also want the best leaving group possible. So the best leaving group is going to be the most stable when it leaves. So bromine is going to be more stable when it leaves. So if you have iodine as the strongest nucleophile and bromine as the best leaving group, because that's what determines the rate, right? Then A is going to be your right answer here. If the question was in acetone or something that didn't have any protons, the best choice would be bromine as your nucleophile, and then the better leaving group between the two of these is chlorine because it's more stable as a Cl minus charge. So this answer is different based on what solvent it's in. So don't just assume iodine's always the best because it's not on the different solvents. Okay, for question 13, which SN2 reaction would take place most rapidly? Okay, so this is all of the leaving group substrates are the same. So we can't eliminate based on that. And they're all in a protic solvent. So we can't eliminate based on that either. So we're looking for what would be the best nucleophile and protic solvent. Well, a better nucleophile is always going to be more negative. So let's get rid of these neutral ones. Now I'm going to hold off on looking at SH because I know we can't compare between atoms always, but we can compare between these same atoms, these two oxygens. So between the two of these, the best way to tell is if you remember, a stronger acid has the weaker conjugate base. So if we're going to compare the acids with these conjugate bases, this is the stronger acid. It's 4 to 5 pKa, and this is 15.7. So this is going to be the weaker base, so we can eliminate that. So now we're comparing OH minus and SH minus. And these are very similar in the same period, like these IBrClFs are. So, and we're in product solvent. So the bigger area for the negative charge to be delocalized around is going to be SH minus. OH minus is smaller based on the atomic radius. So this is going to be more well dispersed. So this is going to be your better nucleophile in product solvent. If we were in a product solvent, if we were in something, a product meaning not product solvent, like acetone or something, this would have been the better answer choice. But if we're in product solvent, in water, you have to look for that. So you have to pay attention to what your answer is based on your solvent. Okay, so the next question, which nucleophilic substitution reaction would be unlikely to occur? So let's look at leaving groups and let's look at nucleophiles. All these are good nucleophiles. OH minus, I minus, CH3S minus, any of those could get the job done. For leaving groups, I is a good one. Hydrogen is not a good leaving group. H minus is not stable the same way I minus is. So I don't think this would be likely to occur. Oh wait, we're looking for which one would be unlikely to occur. So this is probably a good answer possibility. Bromine is a good leaving group. So both of these have all the necessary ingredients. So all of these would be unlikely. This negative is confusing to me, but B would not be likely to occur, so it is the right answer. I think question 15 is a repeat, so we're not going to go over that one. It's the same as question 14. Okay, so question 16. Which best describes the chemical process shown below? All right, so let's talk about that. We can tell right here, just from the fact that a double bond is formed, that it's an elimination. So let's get rid of these substitutions. So the next question is this a E2 or an E1? So based on the fact that this is not negatively charged, I'm going to go ahead and go with this is an E1 reaction. With E1 and SN1, it's so hard to tell which one it's going to be, but we know it's an elimination, so I'm going to go with that. This is also pretty bulky, you know. You have some big groups here. Oh, nitrogen, the CH3, yeah. This is a pretty inhibited one, so the bulky is also part of why it goes towards the elimination. Oh, and part of why, so I should have gone this way. So let's do it from the beginning. We've got our nucleophile. This is not negatively charged and it's bulky, so it's going to go to the one side for sure. And it's also going to go to the one side because we know it's got the secondary or tertiary. So the carbocation will be stabilized. The bulky leaving group makes me think it's an E1. So if we didn't already know the products and we were just looking at the reactants, the nucleophile is weak. It's not negatively charged. And between these, you've got secondary, tertiary. So the fact that tertiary doesn't really give one away, but this is pretty bulky. So it's going to go towards the E1 side. We do know the product, so I don't even know why I was justifying that. So we already know it's an elimination, so we're just deciding between 2 or 1. So it's not strong, it's not negatively charged. It's got a lot of space to share those 2 electrons around. So it's going to be an E1 most likely. Okay, by analyzing the starting material and the products, the following reaction is an example of what? Well, again, we know it's an elimination, so we're really just trying to decide, is this an E2 or an E1, right? We don't have a nucleophile to look at, which stinks, but there's another way. If you look at the things that favor an E2 versus an E1, it is not possible for you to have a carbocation that's primary. It is possible for you to have an E2 on a primary. It's not as likely. Your E2 is probably going to favor a secondary or tertiary, but it is nearly impossible to have a carbocation on this one. So that makes me think not being able to look at the nucleophile makes me think the only thing we have left to look at is the leaving group, and the leaving group is primary, and you're never going to see primary for an SN1 or an E1 because it has to form a carbocation. So the right answer choice is going to be E2. Okay, next question, suggest a reagent to perform the following transformation. Okay, this is an elimination reaction. So we know that already. All the reagents that are given, really we could make this be an E1 or an E2, either one, but all these reagents are given are negatively charged. So it's not going to be an E1 or an E2. This is going to be an E2. And if we have a strong base and a secondary, the only way to shift to E2 is heat, which I would definitely use heat, and a bulky nucleophile. So the bulkiest of them all is the tert butoxide. This is your quintessential classic bulky base. It's really considered to be quite huge and cumbersome. So answer choice D is the right answer. If you ever need a bulky base, always go with tert butoxide. Oh, I didn't see even E as an option for ethanol. So I don't think ethanol would work. Interesting. Let's see. If we used ethanol, this would leave. Oh, you know why it wouldn't work? Because a carbocation would form, and then you would get rearrangement. And that's where your double bond would have to form here or here, and that's not where it forms in this one. So an E1 would not work. Good thing I saw that answer choice E so that I could address that. Okay, question 19. What would be the major products of the following reaction? Okay, well, I'm going to start this the same way I start all of them. My nucleophile is negatively charged. That's strong, so I'm going to go on the 2 side. It could be either an elimination or a substitution. I'm going to say because there's no heat and because it's a pretty narrow, just like a straight chain, it's this, no, I didn't mean to draw on that. It's a straight chain that looks like this. It's not the bulkiest, so I'm going to say this is probably going to favor an SN2. In real life, you'd probably have some of the elimination reaction as well, but I'm going to think it's going to go with SN2. So if you have an SN2 reaction, this is going to attack right on where the iodine is. It's going to kick the iodine out, and you're going to get an inversion of stereochemistry. So your final product is going to be, this stereochemistry is unaffected. This is going to be a dash. I drew way too many carbons here. It's CH2, CH2, CH3. So this carbon's not supposed to be there. So 1, 2, 3 carbons, 1, 2, 3 carbons. It's going to look something like this. So I think your right answer is answer choice A. 2 is a substitution reaction, but that substitution reaction would only be possible if you have an E1 that forms. And if this left and formed a carbocation, it would rearrange over here. So you'd get them both on this same carbon, and you'd have to have a racemic mixture. So it'd have to be a wedge and a dash. So that's not really going to be possible. You need to have the inversion of stereochemistry with an SN2 reaction. For answer choice 3, that's an elimination reaction. So that's a reasonable possibility here, I would say, but it'd have to be an E2 reaction. And with as narrow as this is and no heat, I just think it's unlikely would be my opinion, that you would have an elimination reaction take place. Not impossible, less likely. And then here, there's absolutely no reason for this stereochemistry to invert, so that's not going to form. So the only possible answer is answer choice A. Or none of these choices, I guess. But there is a possibility for answer choice A, so I would go with that. And it is important to note, it asks what the major product is. If it asks what are all the products possible, then both of these would be right. But it's not asking what are all the products possible. It's asking which one is the major. Okay, next question. Which would be the major product of the following reaction? Okay, this big crazy thing, what is that? This is what's known as a Tosyl group. This is a good leaving group. So whenever I see Tosyl groups, I replace it with just the word Lg. A similar structure that's also just a good leaving group is a mesyl group. It's a methyl right there instead of the, this is called toluene, so that's why this is Tosyl, this is methyl, so that's why it's mesyl. Toluene, Tosyl, methyl, mesyl. That's how they come up with those. Doesn't matter. Whenever I see those big crazy structures, I just put Lg right there. Leaving group. It's going to be a good leaving group. And it's reacting with SCH3 minus. That's strong, so it's probably going to be an SN2 or a 2, SN2 or E2. It's secondary, so it could go either way. There's no heat, so I'm going to guess with a strong nucleophile, no heat, not really bulky, it's probably going to go for SN2. So this is going to attack and kick out your leaving group. And remember, the stereochemistry gets inverted, so SCH3. So the right answer would be answer choice C. This would be for an elimination reaction. I think you just need a bulkier nucleophile and some heat to make that happen. Same thing with answer choice D. And this one is fine. It just doesn't show stereochemistry, so it's not the best answer. And realistically, I do think you'll get some of these products, but they won't be the major product. This would be the major project. Okay, answer C. What would be the major product of the following reaction? So all of these are challenging because you really have to be able to tell if it's going to be substitution or not. And then you also have to be able to tell substitution elimination, SN1, SN2, E1, E2, and you need to know the mechanism, and you need to figure out the product. And a lot of times that requires also involving stereochemistry. So these are complex problems. So if you're having a hard time with them and you need to slow down, that's okay. And be sure to do that and pause the video and try and see if you can figure it out and try finding other practice problems to work as well. So in this case, N3 is going to be N3 minus. So this N3 is strong, so I'm going to assume it's going to be 2, either SN2 or E2. Let's see. There's no heat, and that N3 is pretty narrow. I think the structure is literally something like this. Not positive. But it is going to be pretty narrow with just 3 nitrogens. So I'm going to go with a substitution reaction, so SN2. Again, in reality, probably some of the others would form, but it's asking what the major is. This is another good leaving group. It's like a Tosyl or a mesyl. It's just got CF3 instead of CH3 here. But you can recognize the oxygen with the sulfur, 2 oxygens, and then whatever this group is here. So that's just a good leaving group again. So if it's easier to visualize, we'll draw just leaving group, and then the N3 minus will attack here and kick out. So you're gonna, if it's an SN2, it's an inversion of stereochemistry. The other one doesn't change. So the right answer would look like this. And that's, 3 almost got me because it has a wedge there. We're not looking for that. We're looking for a dash. There's no reason for this one to change. So there's not a right answer. Oh, they got me. I almost got. This one, the big issue is this oxygen is still there. So that's kind of the biggest problem. Okay, For 21, predict the product for the following reaction sequence. H minus is what this is. So actually this is an acid-base question. So this is H minus. It's going to steal this and make this product, this O minus right here. So to make sure that this is actually going to happen, you just need to remember the acid-base reaction that we learned. This pKa is 16 to 18. This pKa is 35. We're going from a stronger acid to a weaker acid. So that is great. So that first step, that's all it is. Then we're adding 1 iodopropane. When I see 1 and I know it's going to be primary, that tips me off that it's probably going to be an SN2 reaction, but we'll see. 1, 2, 3, and we draw an iodine there. Yeah, this is a strong nucleophile that's attacking a primary. If it's a primary, that's usually going to be SN2. Like basically primary leaving group at all would be SN2 because you can't have a carbocation on a primary. So that is always a good indication. So our final product ends up being like this. So this is combining what you learned in the last chapter. 1, 2, 3. Oh, I lost a carbon. So answer choice A. So this is combining what you learned in chapter 3, where you're doing acid-base reactions first, and then this is called a multi-step reaction. You're using the nucleophile that you created with an acid-base reaction to attack a substrate. Okay, so for question 22, we're going to predict the products for the following reaction sequence. So, oh wait, this is the same one. Repeat offender. Not going to go over that one. 23, what would be the major products of the following reaction? So this is a Tosyl group, so I'm just going to write leaving group. Ooh, so we've got a strong nucleophile and heat. So that goes, strong makes it go to the 2 side of the chart, and heat makes it go to the elimination. So it's E2. So you can lose a proton from here or here. What I mean by lose a proton is when you have, your E2 reaction, your nucleophile is going to take your proton, it's going to form a double bond and kick this out. Or if it takes from the other side, the nucleophile will take a proton, form a double bond, kick this out. So your 2 options are like this. And in the next chapter, we'll talk more about how you can make it go to one or the other. There's ways you can control that. We're not going to talk about that till chapter 7 though. So, and I really actually like that stuff. It's called Hoffman's site stuff, and it's really fun. So these 2 would be your possible products. And they would probably happen about 50-50 with this setup. Like I said, we'll learn more how to control one to the other, but these are pretty equivalent. So I think answer choice D is the right answer. Okay, remember how I was talking about bulky bases and tert butoxide? Looks like this. You often see it abbreviated tert, butyl, oxygen, and a K group. So the K is just a plus charge. So tert butoxide or potassium tert butoxide is going to be a big, bulky base. Sorry, I just lost my train of thought. I'm tired, can you tell? So we've got our big, bulky base. So that tells me definitely we're going to have an elimination of some kind. It's got the negative charge, so it's strong, and it's bulky. So I'm assuming this is going to be an E2 reaction. So our leaving group is here. There's actually only 1 hydrogen adjacent to where our leaving group is, so there's only 1 possible product. If there was a methyl group over here or something, you could get a double bond here or here, but in this case, the only place to steal a proton from is here. So this is going to take a proton, it's going to go right there, this leaving group is going to leave, and you're going to get answer choice A as your right answer. Okay, for question 25, which would be the major product of the following reaction? Okay, so minus charge makes it go to 2. The heat makes it go to E2. So this is another elimination question. Our leaving group is right here. So you can either lose your proton from here, or technically here, but because this is symmetrical, that's the same one, or here. So there's 3 places you could lose it from, but 2 are the same. So your nucleophile is going to attack this proton. The electrons are going to go here, and the bromine's going to leave, and that's how you'll get this product. And I'm losing the wedge. It's just a flat line now because this is sp2 hybridized, and sp2 hybridized is flat. It's not tetrahedral. There's only 3 things attached, so it's going to be planar. The other side still has 4 things attached, so it still has its wedge and dash. The alternative is for the proton to steal from here, double bond to be formed there, and kick out the bromine. And that structure would look like, again, the far side is not impacted at all. We would have a double bond right here. So that's answer choices 3 and 4. So C would be the right answer. Okay, the last question, 26. The product for the following reaction would be mainly dictated by which mechanism? Okay, well, we've got ETO minus, so that's a 2, definitely. It's narrow and there's no heat, but this is a tertiary leaving group, so I'm going to say it's going to go E2. And we don't even have to. It doesn't ask us to solve the problem, but if you wanted to, base would abstract from here or here. You could go here, but these 2 are the same. So your final products would be... And that's something I like to do. If you feel like you know the answer to these, no problem. You'll notice I not only solve the practice problems, but I also sort of reason through them. And so I, just to test myself, will go one step further. I'll go through every one and say, how could I have gotten this? How could I have gotten this? Why is this wrong? I'll go through all of them. That's something for you to work on if you feel like you need more practice problems as well, or if you want to check yourself, or just whatever, however that will help. Okay, well, I'm so sorry this video took a little bit longer than normal, but I hope it's helpful to you guys, and good luck studying for your exam.